Good morning. Let us continue with our third day and the third lecture by Sam Grushevsky. It's good to see so many eager faces here.
So thank you for coming back. Remember, there are no exercise sessions today. Mathematically, you have a much more important exercise, which is going up the Great Wall. You are supposed to do all the math exercises while walking. So they will, whatever I assign as exercise must be something that can be done without a piece of paper. Let's remind ourselves where we were. So for us, C is a curve of genus G, and it has a Jacobian of C, which is peak G minus 1 of C, which, as we discussed, is isomorphic to peak node or peak anything else of C. And inside that, there is a theta divisor, theta, okay, which is the locus of all divisors of the form P1 plus dot 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 plus Pg minus 1. So this is the locus of what are called effective divisors in here. A divisor is called effective if it's a linear combination of points with positive coefficients. And we have Riemann theta singularity theorem, which says the multiplicity of a point theta of the divisor theta at a point L is equal to the dimension of H naught of CL. Of course, I'll write very quickly little h naught for this dimension. Okay, let's parse this again. So this is for any L, which is a degree G minus 1 line bundle on C. So for any point in the Jacobian, in the peak G minus 1, a point corresponds to a line bundle. This is a divisor. I'm trying to ask about its multiplicity at the point, so I can take the maximal ideal of this point and try to see in what power of this ideal the defining equation of theta is contained. And this is a formula that tells us that this multiplicity of a theta divisor is a codimension 1 subvariety of peak G minus 1. This is G-dimensional. Is equal to the dimension of the space of sections of the line bundle L on a curve. So what this does is it relates the geometry of the curve. This is manifestly on a curve. I'm thinking about a line bundle on a curve and how many sections does that object have versus the geometry of the Jacobian. That's why this is so useful. And what we're going to talk about today is how to see from this some interesting property of Jacobians. And that's what I will do now. But before I do that, let me say what the plan is. So we'll discuss today the trisecants of Jacobians, and I will be able to state finally the theorem of Krichever, which is the main goal of this lecture series. And you'll finally know what the statement is because I will have written all the words on the blackboard. After that, we'll switch gears again, and we'll go back to differential equations. And instead of going straight to differential equations, I'll talk about functions on curves with an essential singularity, which you have seen in Pasha's exercise sessions last evening, hopefully. But there will be a so-called Baker-Hieser function, and I'll introduce what that is. And the goal will be to show that this Baker-Hieser functions provide some solutions of some differential equations. And then we'll eventually continue to see what solutions they provide and work further with that. So that's the plan. But for the next 45 minutes or so, we're still going to be doing algebraic geometry. So raise your hand if you're becoming more familiar with algebraic geometry as we go along. So that should be everybody, right? If not, I'm not doing a good job. You don't have a choice. If you're not raising your hand, ask questions. I mean, do ask questions. So, there is this Schottky problem of characterizing Jacobians among all abelian varieties. Keep it in the back of your mind. We're not there yet. This will be on the blackboard in an hour. So my next goal is just to prove a theorem. This is called Way reducibility. Raise your hand if you know what this theorem is. Good. I finally reached a significant point in this lecture course. I do know, and I'll tell you. It's not a difficult theorem. It's very surprising. So I'll write the theorem, then we'll remain confused about it for 5 minutes, and we'll discuss why it's very strange, and then I'll actually prove it, which will not be a big deal. So I have a curve C, I have the Jacobian, which I'm thinking of as peak G minus 1. It says the following. It says for any curve C and for any points, which I'll denote P, Q, R, S, which are points on C, the following holds. I can take the theta divisor. That's a divisor in the Jacobian. I can take the theta divisor and translate it by P minus Q. So what this means, translate by P minus Q of the theta divisor. What does this mean? So theta is a divisor. It's a locus of points in peak G minus 1. Take any point in peak G minus 1, add to it a divisor P minus Q. That's also a divisor of degree G minus 1. Consider the locus of all such. If you're thinking of the Jacobian as an abelian variety, it has translations. I can translate. More precisely, P minus Q is a divisor of degree 0. So this is peak 0 acting on peak G minus 1. So what did I write here? I wrote a theta divisor. It's a G minus 1 dimensional gadget in a G dimensional abelian variety. That's another G minus 1 dimensional gadget in a G dimensional abelian variety. So there's two big codimension 1 things that intersect. They're codimension 1. I haven't told you, but it is true that for Jacobians, this is irreducible, indecomposable, not a union of two things. So they don't share a common component. That's irreducible. So the intersection is going to be codimension 2, right? We have two complex codimension 1 things. Their intersection in complex codimension 2. I'm not saying that this thing is irreducible. That's exactly the theorem. The theorem is that this is actually never irreducible. So more precisely, this intersection is contained in theta P minus R. Let me check that I'm keeping my notation consistent. Theta S minus Q. So these are the same kinds of translates, right? I take a theta divisor, that's this is a set of effective divisors of degree G minus 1, and I add to each of them P minus R. That's the same here. So maybe I put parentheses here just so that you can read more easily. Something very strange is written on the blackboard. We'll prove this, trust me. But something strange happens. Look at the left-hand side. I take the theta divisor, well-defined, unique, no choice involved. I just told you what it is. I translate by P minus Q. So I get some codimension 2 thing, which depends on P and Q. Sorry. And then I claim that it is contained in the union of two codimension 1 things. All very nice, except the points R and S only appear here. They don't even appear on the left, right? So what I'm telling you is that this codimension 2 thing is contained in a whole family of such things. Just fix S, let R vary. This thing will move, right? But somehow the union of these two things will still contain the intersection. If you remove either piece, this is false. This is verifiably false. But this is true for any P, Q, R, and S. And what is so surprising is this thing moves with two parameters, R and S. So I'm defining for you a two-parameter family of unions of two theta divisors so that the unions always contain this intersection. So this intersection typically will have two components, one contained here, one contained here. Okay? This, if these points are not distinct, this is boring. Because if, say, P is equal to R, this is just the theta divisor. So this is true, but boring. Right? If P is equal to Q, this is just the theta. Maybe P is not equal to Q to be safe. Okay. I don't want to think about it. So the interesting part is when P is not equal to Q. You can make sense of this in the limit, which we'll do in a second, but not yet. Sorry. I could take the intersection of this over all R and S. I'm not doing this. I'm not making any claims in that direction. No. Okay. Is the statement clear? So I have a divisor. This is a set of degree G minus 1 divisors, which are sums of arbitrary G minus 1 points. And I add to all of them P minus Q here. It's another divisor, which can be of this form, right? I mean, this is up to linear equivalence, up to divisors of functions, right? So if I write P1 plus dot 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 plus PG minus 1 plus P minus Q, it could be that if I choose different points, this will be of the form, you know, x1 plus xg minus 1. That's what this is about, right? This is intersection in Jacobian. So that's the Weyl reducibility. This is a very surprising thing, because you would expect, if you're in a very general situation, everything as generic as possible, you would really think such intersection should be just irreducible, should have just one component. And then it's not going to be contained in either one. As you'll see in half an hour, it's very clear that something like that is manifestly false. So you do have two components, one contained here, one contained here. Okay? Any questions on this statement? This is due to Andre Weyl. Proof. So the proof uses just Riemann theta singularity theorem, nothing else. So suppose I have some divisor D, which is a class of some line bundle. So this is, I'm writing D for a divisor, and this is the corresponding line bundle. It's a class of a line bundle. Suppose this is a divisor which sits inside this intersection. I want to check that then D sits on one of these two, right? That's what I'm asked to do. What does it mean that this sits in this intersection? Well, D, it's a divisor on C. This is a line bundle on C. I'm sorry. So I'm trying, I mean, maybe I shouldn't, but I tried for once for a second to be pedantic about distinguishing divisors and line bundles. So it's a divisor on C, so that's an element in peak G minus 1, which I'm thinking of as a class of a line bundle, as an equivalence class of a line bundle. It sits both here and here. So what does it mean that D sits in theta? Well, D sits in theta means, of course, that I can write D as a sum of points, but I don't want to write that. This means this is a Riemann theta singularity theorem, Riemann theta singularity. Hopefully, this is a recognizable enough notation. This means that the multiplicity of theta at the corresponding line bundle is at least 1. This means that H naught, remember this is the dimension of H naught, of CL is at least 1. Right? That's the definition. What does it mean that D sits in theta translated by P minus Q? This means that H naught C L plus, now I'm mixing notation, right? But CL plus P minus Q is also at least 1. I'm being very sloppy about whether this is P minus Q or Q minus P, but my convention is that this means that. So maybe I'm really translating by Q minus P, I don't know. Okay? Doesn't matter. As long as I do it consistently, it's all fine. Maybe all the signs are flipped. Okay? So what does this mean? How should I read this? So these are, if I sort of write a D here, this means this are the sections, these are meromorphic functions on C that may have poles at D, may have a pole at P, and must vanish at Q, right? So let's try to understand what is the dimension of the space of sections of D plus P. So what are these again? So these are meromorphic functions on C with poles at D, simple poles, and a simple pole at P, vanishing Q, right? I mean, a section of a line bundle, a meromorphic section of a line bundle, a holomorphic section of a line bundle is a meromorphic function on the curve with given poles and a given vanishing. So let's understand what could this be. So what are these things? These are meromorphic functions on C with poles at D and poles at P. So this is certainly at least equal to that, right? Because if I am required to have a 0 at Q, well, if I'm not required to have a 0 at Q, I'm still this. This is also at least equal to that because I'm now allowed to have a pole, right? Let me write D here because I'm thinking of this as divisors. Okay? So let's try to go through both cases first. So if H naught of C, D plus P is equal to 1. So this means basically that there exists unique up to constant section, up to constant factor, section S in this space which is to say S is a meromorphic function with poles at D and a simple pole at P. Okay? But this function is unique. Then this implies that S must vanish at Q. Because this space of sections, so this is just sections of this that are required to have a zero. But this is non-zero, so there must be a section here, but then it must be the section that I have already seen. There is no choice. Okay? Very good. So in this case, but then, now I should, let's see what I have. So I have a section S, which is going to vanish at Q, right? But I also must have, this is contains this, which is also non-zero, right? So I must have a section here, but then it must also be S. So thus, S has no pole at P. So this means that in reality, S is really a section of D minus Q, because it does not have a pole at P, and it does have a zero at Q. But this is, of course, contained in C, D, which one did I use here? S minus Q. Okay? But this means that the multiplicity this means that multiplicity of the theta divisor translated by S minus Q at the point D is also at least 1, which is to say that D just lies in theta S minus Q, right? I mean, the fact that this is not 0 by definition means that this is a point of the theta divisor translated by S minus Q. Okay. Let me do the second case. So this was case 1. Case 2 is if this space of sections is larger than one-dimensional, right? So if it's larger than 1, the next integer is 2. So this is at least 2, right? So if I have 2 sections here, so suppose I have 2 sections, S1 and S2. Suppose there are 2 sections non-linearly dependent. Okay? But then there exists a linear combination alpha S1 plus beta S1 for some alpha beta complex numbers, such that this linear combination evaluated at the point R is 0, right? Because these 2 sections at a point, they just give me some values. I can just take the ratio of their values, well, with a minus sign, right? So alpha over beta should be equal to S1 of R, S2 of R over S1 of R with a minus, right? That's what I need to do. Oh, yeah, so the S here is a point, the S here is a section. That's a nice, nicely written S, okay? That's a nicely written S. For the notes, should be better. I'm sorry. Okay. So this means alpha S1 plus beta S2 is then a section, well, of the same bundle. If they both vanish at R, I'm delighted. I choose either one. That's fine. So if S1 of R is 0, choose S1. Choose. Okay. Which is to say that D lies on theta P minus R. That's it. So I've written the proof now. Let me go over what happened here. So how am I thinking about this? This is the space of all divisors D which have a section, which means this is a space of all divisors D such that there exists a meromorphic function on C with poles at D. This is a space of functions D such that there exists a meromorphic function on C with poles at D, a simple pole at Q, at P, additional pole, maybe higher order if P is part of D, but never mind that, and a 0 at Q. This is a function, this is a space of D such that there exists a meromorphic function with poles at D, pole at P, 0 at R. Poles at D, pole at S, 0 at Q. Okay? And what am I really using? I'm using the fact that if I look at the space of sections of D plus P, I look at the space of meromorphic functions with poles at D and P. That contains both this because I've allowed an extra pole at P. This contains this because I'm not requiring to have a 0 at Q. But if both of this, if I have a divisor D which lies on both of this means I have a section with poles only at D, but I also have a section with poles at D, a pole at P, and a 0 at Q. But morally, adding a simple pole can add at most one dimension. Subtracting a 0, requiring a 0, can subtract at most one dimension. And that's what I did. So I said, if I have something here, let's look at how many sections the divisor D plus P has. It really has at most 2 sections, because I've added just a simple pole. If it only has 1 section, since this contains a space of sections that vanish at Q and a space of sections that do not have a pole at P, this one section must really not have a pole at P and must automatically have a 0 at Q. So this means I then have a section of D minus Q. Okay? But then in particular, I have a section of S minus Q. So this, you see that in this case, I am really proving that D minus Q has a section. I cannot phrase that in terms of the theta divisor. This is a divisor of degree G minus 2. I have no idea how to think about it. This I can phrase in terms of theta divisor. On the other hand, if this guy has at least 2 sections, then by requiring a section to vanish at the point R, that's at most one condition. So I'll have still at least one section of D plus P minus R, in which case I lie on that divisor. End of proof. Any questions? So what really is happening here is I'm thinking of something I didn't spell out very carefully. And that's somehow, I'm thinking of sections of line bundles and meromorphic functions on Riemann surfaces interchangeably, right? A meromorphic function with prescribed divisor is a section of this line bundle given by this divisor. That's what I'm using over and over again. That's the end of the proof. The only thing I use is Riemann's theta singularity theorem. Nothing else really, right? It's completely elementary. Let's try to understand what Weyl reducibility means analytically in terms of functions. It means the following. What does it mean that if I have for Z, which is in C to the G or in the Jacobian, if you wish, but I'm preferring to think C to the G. What does it mean that Z lies on the theta divisor? It means theta Z of Z is equal to 0. What does it mean that theta lies there? It means and theta of Z plus P minus Q is equal to 0, right? That's how I interpret the intersection, right? It means that both of these are contained. This means that either theta of z plus p minus r is equal to 0, or theta of z plus s minus q is equal to 0, which is of course the same as to say that the product is equal to 0. That's the statement I get, right? So analytically, the statement is that if this function vanishes at z, and this function vanishes at z, then the product of these two functions vanishes at z. Okay? It would be lovely to somehow write something better than this. I'd love to write an equation. Okay? How can we imagine that this happens? So I want to write some equation that will imply that, and then we'll worry whether it's equivalent. So I have two functions, this one and that one, and if they both vanish, that function should vanish. So somehow if you are motivated by ideals of functions or something like that, that should mean that this function sort of should lie in the ideal generated by these two, right? That if this one vanishes and that one vanishes, that one vanishes. Okay? So one way for this to happen is if there exist functions f of z and g of z such that f of z times theta of z plus g of z theta of z plus p minus q is equal to this. Okay? Then this would certainly imply that statement, right? If I have an equation that says such a combination of these two functions with some function coefficients is equal to that, then of course if this vanishes and that vanishes, this better vanish, right? So now I was writing this as functions on c to the g, but these are really functions on an abelian variety, right? So what is this a section of? This is a section on the Jacobian of some line bundle. Let's figure out what line bundle this is. Well, what's the line bundle? I have a theta function, it's a section of theta. I have another theta function, it's also a section of theta. So altogether it's a section of 2 theta. I'm using the algebraic geometry's notation for line bundle. So 2 theta is a theta tensor square. And then there is a translate. So let me write this better so that you can read. So the right-hand side here is a section on the Jacobian of the 2 theta bundle. So 2 theta is theta tensor squared, shifted by everything. Right? As a function on the Jacobian, this is a section of a bundle theta shifted by p minus r. This is a section of the bundle theta shifted by s minus q. Altogether, it's a section of 2 theta shifted by everything altogether, right? What is this guy here? Well, this is a section of theta shifted by p minus q, right? So this means g, for this to work, one way for this to work is this better be an equality of sections of line bundles on the Jacobian. So this guy here must be a section of this bundle minus that bundle, right? So I would expect that g of z is a section of 2 theta shifted by p plus s minus r minus q minus theta shifted by p minus q. But this is, of course, just theta shifted by s minus r. Okay? What is theta shifted by s minus r? What are the sections? Well, there's the theta bundle, which is just chosen to shift somehow. The theta bundle has one section. Its shift has one section up to scaling. So this means that what I really want to get, let me maybe go to the other blackboard. Let me go here. Yes? What I mean by this? Okay, so, 1 second, no. So you're asking, what do I mean by 2 theta p plus s minus r minus q, right? That's what you're asking. So by this, wait, okay, I got your question, I think. So what I mean by this, I mean I take theta, I take its tensor square, this is a line bundle, I take its square, and then I tensor it by O of p plus s minus r minus q, which I'm just writing as p plus s minus r minus q. This is a line bundle in peak node, right? And then what this means is, I mean, I take tensor square of theta, tensor this O, minus means tensor theta inverse, tensor, so, and then minus theta s minus r means theta tensor O s minus r inverse. Okay? Say it again. What is defined on the curve? These are line bundles on the curve. These are all line bundles on the curve. Well, these are all line bundles on the curve C. This is a bundle in peak node, right? The Jacobian is line bundles of degree peak G minus 1. But a line bundle on degree, I mean, peak K is still a line bundle on the curve of degree K. Okay? So let me try to write the next thing. So what I'm trying to say is I have on the right, so I'm looking at this equation up there. So I have this. Okay? I don't care. I care about the line bundle on the curve. Okay, these are all line bundles on the Jacobian. Yes, I mean peak. The Jacobian is a principal of polarized abelian variety. Its pk is a dual abelian variety, which is canonically identified with Jacobian. The pk of the Jacobian is equal to the pk of the curve. Okay, I never said any of this. Let me write the next statement, which is all I want. Okay, so I want to say the following. So I want to say that if I have this theta of z plus p minus q here, what I really have to multiply it is by some section of theta translated by s minus r. But this is just to say I multiply it by theta of z plus s minus r, right? But there is a constant which I'll call capital B, okay? So B is a constant. And that's what that expression here has to look like. The first expression here, I have theta z plus, and then this must be theta, and if you compute it, just the total shift. And then there must be some A. A, B here are complex numbers, okay? And this implies that, right? If I have such an equation here, then that equation there holds because I just prescribed that the functions capital F and capital G are of this form. My mumbling here about line bundles indicates that this is indeed equivalent. Okay? Moreover, more work, and not just mumbling, indicates that this is also equivalent. Okay? And for that, I need to compute some Kozulkov homology, which I'm not going to compute. Okay? So altogether, what this says is that Weyl reducibility, which is a theorem we just proved, is equivalent to this equation. Okay? So Weyl reducibility, which is this geometric statement that the intersection of two theta divisors is contained in the union of two other theta divisors, is equivalent to an actual equation satisfied for a theta function, globally for all z. That's the message of this discussion, right? I haven't proven this, so it's clear that this equation being satisfied implies Weyl reducibility, right? Because if that's true, if theta vanishes and if this vanishes, then certainly that vanishes, right? I claim that this is an if and only if. My mumbling here was to indicate a path to try to do this, but this requires serious work. Okay? Any questions here? This is an equation for a theta function. It's a functional equation, right? This must hold for some AB. AB are going to depend on P, Q, R, S for all I know, but they don't depend on Z. That's the point, right? They're constants. They're, as functions of Z, they're constants. This A depends on P, Q, R, S. Maybe I should suffer and put a C here, which will also depend so that it looks more symmetric, but never mind. But this is an equation that must hold for any Z, well, in C to the G or in the abelian variety, up to you, doesn't make a difference. So this somehow means that if I have a Jacobian, and if I choose an arbitrary quadruple of points on the curve, then I have a functional equation of this form satisfied by the theta function. Okay? What is this equation? Where does it take place? Well, now everything here is a section of this bundle, 2 theta translated by stuff, right? So this is an equation of three sections, this one, this one, and this one. This 3 sections of the line bundle 2 theta with this shift are linearly equivalent. So that's an equation of 3 different sections of the bundle 2 theta. Okay? 2 theta is the square of the tensor square of the bundle theta. You know that the bundle theta itself has only one section. Let's try to understand how many sections does the bundle 2 theta have. Okay? Let's try to understand this more. So the goal now is from this, I want to get this a functional equation, which is what I'll really use. But I'll want to extract a different geometric statement from that, which is a nice geometric statement. For the actual proofs, eventually, you'll see what we'll use. It will be closer to actual equations. But any questions so far? So the claim I made, I didn't write the theorem. The theorem is Weyl reducibility is equivalent to this holding for any PQRS. Okay? But I don't want to write this. This is not a nice looking theorem. But not a geometric. It's a nice looking theorem. It's not a geometric statement. Okay. Fact. For any principally polarized abelian variety, A with polarization theta, the dimension of the space of sections of the bundle 2 theta is equal to 2 to the G. Okay? Here is a quick proof which I won't write. So what is this H0? Theta was an ample bundle. H1 vanished, right? So the fact that H0 of theta is 1 means theta to the G, the top self-intersection number, is G factorial. But the top self-intersection number of 2 theta differs from the top self-intersection number of theta by a factor of 2 to the G. H1 is still 0, so the Euler characteristic just scaled. Okay? So that's a statement, and a basis of the sections. These are ample bundles. They don't have any higher homology. Okay? I need to mumble something to convince you. It's true. Okay? I can tell you what the basis of, what I really care is not this, I care in the fact that there is an explicit basis, maybe. Up to you. I don't care about this, I don't care about explicit basis, I care about what will show up in a minute. So there are no higher homologies for polarizations in the abelian variety. That requires a proof, but it's not hard. In principle, ample bundle, it's not very, theta is not ample, 2 theta is almost very ample. It's very ample on a finite quotient. I'll be fine. Okay, is given by the following. So I'm supposed to give you a basis of the space of sections. So I'm supposed to write for you 2 to the G functions, and these are the so-called theta constants of the second order with characteristics. I'll write what they are. We won't really care so much what they are, but I care that they exist because I want to do something here. Okay. I apologize for the notation. This means a theta function, not a theta divisor. There is no other notation, but it has this epsilon thing. So epsilon is a vector of g zeros and ones. Okay? And then what I do is I take a theta function, I evaluate it at 2 tau and 2z, which I shift by a 2 torsion point sort of. Okay? The way I've written it, it's not at all clear. I mean, it's clear if you do a little computation, but it's not immediate that this gadget here has anything to do with sections of 2 theta. In fact, it does. Okay? It's not at all clear that this gives me a basis for sections of 2 theta, but in fact they do. I multiplied tau by 2, but I didn't put 2 tau epsilon here, right? So this is a 2 torsion point on the 2 tau abelian variety. Okay? But I have somehow broken the symmetry. I haven't taken the epsilon itself, right? I mean, I could shift by 1/2. I'm not doing that. Okay. Huh? That's a fact. It's a claim. I have to prove it for you. Meaning I won't prove it, but you need to prove it. It's not at all clear that this is how it helps us. I'll write a theorem now which will sort of explain. Sure, I could do that. No, but I'm not going to do this. I mean, I know what you said. I can also, exercise, which you cannot do while working on the Great Wall. Take this guy and see how it transforms under the translation by period made, by the periods of tau. And you'll check that it transforms as a section of 2 theta. That's not, but you need to know that there is some representation theory. I've never defined the theta group or anything of the kind, right? And I'm not going to, so. The fact that these are sections is elementary. I mean, you sit down, you write one line. The fact that they are basis for sections is, I mean, you need something, okay? Next fact, if this was the only thing I was not covering in the course, you know, I'd be doing very well. This is called the isogeny theorem, but the specific case I'm doing is called Riemann's bilinear relations. And it's a formula. It's a formula that says if I take the theta function of tau x plus y, and I multiply it by theta of tau x minus y, then what I'm going to get is I'm going to get a sum over all epsilon of theta epsilon, and as above, the sum is over 0.2 of x times theta epsilon of y. Okay? This is called the isogeny theorem, and much more generality. Let me explain, let me say 2 words about where it comes from. So why is it called an isogeny theorem? It's called an isogeny theorem because if I take an abelian variety A times itself, there is a very interesting map of it to A cross A. It's a very interesting map that sends a point x comma y to the point x plus y and the point x minus y. Let's call this map pi for good measure. What is this map? This is certainly a linear map of abelian varieties, right? It's an isogeny of abelian varieties. It's a finite map of abelian varieties. It's a map of finite degree. It's surjective and it has finite degree. What is the kernel of this map? The kernel, what are the points that map to 0 here? So when does xy map to 0? Xy maps to 0 if x is equal to y, and then if 2x is equal to 0. So the kernel are 2 torsion points, right? 2 torsion points on the diagonal. What you can ask, if I take the pullback of the polarization, this guy has a natural principal polarization as a box product of principal polarizations, right? So I have a polarization here, which is trivial on the other projection, and I have a polarization here, and I take the tensor product. Do you know this notation? Okay. I mean the following. So A times A has 2 projections, P1 and P2 to A, which has a polarization. And this is just the pullback of theta under the first projection, the pullback of theta under the second projection. Okay? So this pullback is 2 theta, 2 theta. That you can easily check. Okay? So how does this relate to this? Well, this is a section of the theta bundle here times the theta bundle here. So this guy is a section of this, right, by construction, pulled back to here. And this is supposed to be a section of 2 theta as a function of x, and this 2 theta as a function of y. And I've written a formula. The importance is that it's not just some section that I have no idea about which it is. It's a very explicit formula, right? Okay. Proving this formula, there are good ways to do it, which I'm not going to tell you about. There is a bad way to do it. You just compute. Okay? This is a very straightforward computation that you can do. This is not how you should do it. Of course, you should learn about the isogeny theorem in general and do it that way. But in principle, this is extremely explicit. Okay, let me tell you something else. Another fact, Lefschetz theorem. Take an abelian variety and define a map from it, p to the 2g minus 1, given by the linear system 2 theta. By which I mean you take a point z and you send it to the set of values of a basis of sections of 2 theta, right? That's a map given by a linear system 2 theta. And the claim is, let's not call it F. Let's call it cum. So this is called the Kumma map in honor of Kumma, who of course studied its image. So the claim is cum defines an embedding which I'll still denote by cum of quotient of A by plus minus 1. Okay? So these guys are all even functions of z. That's trivial to check. Okay? So certainly I cannot, so the value of this map at z and minus z will be the same. The claim is that these are the only points which will have the same image under this map. The statement, the full Lefschetz statement would be if I go to any higher multiple, to 3 theta or higher, then this 3 theta or 4 theta linear system is very ample. It defines an embedding of an abelian variety. This is almost that up to this plus minus 1 business. Okay? This is not trivial. I'm not clear saying this is something you do a short computation and you're done. Far from. This requires technology, which I'm not developing. Question, yes? The plus minus, so I have a map from A to itself. For any abelian variety, I have a map from A to A that sends z to minus z. And I take a quotient by this map. Warning, this quotient is not going to be smooth. It's going to be singular at the 2 torsion points. I don't care. I mean, I do care, but not for this theorem. More questions? Oops. Of course, I just erased exactly what I did not want to erase. I'm sorry. Yeah, so for g equal, let's start with g equal to 1. So for g equal to 1, what you get is you get an elliptic curve quotient by plus minus 1 being mapped to P1. Well, you actually know that an elliptic curve is a double curve of P1 branched at 4 points. The 4 points are the two torsion points. Yay, that's the map. In genus 2, as Pasha is saying, you get a surface, an abelian variety quotient by plus minus 1, which is called a Kummer surface, which has 16 interesting double points, which is embedded by this map in P3. You can write an explicit equation for the image. You can study the moduli of abelian surfaces via this map. You can write a book. And if you do, you won't be the first. So there have been books written. If you write this map in genus 3, the geometry becomes very complicated because you have a threefold embedded in P7. There are many equations for this. There are papers being written on this. I'm guilty of that also. But it's a complicated map. Okay. Let me copy the equation I had before on the blackboard, and please correct me if I don't write it well. So we know that Weyl reducibility was equivalent to the equation A theta of z, theta of p plus r minus s minus q, plus b theta of z plus p minus q, theta of z plus r minus s is equal to, let me put a constant here, just so it looks prettier, okay? And let me put a constant with a different sign here, theta of z plus p minus s, theta z plus r minus q is 0, right? That's the equation that I erased from this blackboard a while back, except I made it more symmetric, right? I put an extra constant here, which of course I can divide by, Thank you, okay? So it's the same equation, I just wrote it more symmetrically in some way. Okay, but now use Riemann's bilinear relations. So what do I mean? I use this stuff here, right? So I'm going to write what I get here. So I will be very unhappy to write this every time, right? So I don't want to write this. So I'll introduce notation. This will be the Kummer map of x dot, which means sort of the scalar product, Kummer x map of y. Fair enough? I'm perceiving this as a vector in C to the 2g, and I'm taking a scalar product. This is a shorthand for this notation. Fair enough? Okay? I don't mean anything more. I don't want to say there's some interesting structure. There isn't. It's just my shorthand. So I want to rewrite this. So I get A times the Kummer map. Well, somehow my variables are different, right? There I have something interesting here and something interesting here. So I really want to go from this pair of variables to this pair of variables, right? But this is obviously the half sum, and this is obviously the half difference. And I'm aware that I cannot well definedly divide by 2 on an abelian variety. I couldn't care less. I'm dividing it in C to the g. I mean, I should care, but I'm not worrying about that. So this will be the Kummer of the half sum. So the half sum will be z plus p plus r minus s minus q over 2 dot Kummer of the half difference. The half difference, the z cancels, so I just get p plus r minus s minus q over 2. Okay? No, that's the whole point. So I'm supposed to take a half sum of these things. So the half sum is 2z plus junk. So it's divided by 2 is z plus junk. The half difference is just the junk without the z. Thank you, Pasha. I was hoping somebody would ask that. Okay, plus b times the second thing. So what's the half sum? The half sum is 2z plus p plus r minus q minus s. It's the same. Well, when you use this, it's going to be the same. It's a section of the same bundle. So it's the same expression times the Kummer of the half difference, p minus q plus s minus r minus q over 2. Okay? third C times the Kummer. Well, I hope we have learned by now that the half sum will be the same because it's actually the same bundle. So it's the Kummer of Z plus P plus R minus S minus Q over 2 times the Kummer of half difference okay? What do we see? Of course, what we write here is Kummer of Z plus P plus R minus S minus Q over 2 times stuff is 0, right? So that's what this says. There is a common factor. What does this really mean? And this common factor is independent of Z. And this is true for any Z, right? But these guys, well, shifted, doesn't matter, are a basis of sections of 2 theta. They are bases, they are linearly independent. They don't satisfy any linear relations. So this is equivalent to saying that this stuff is 0. Okay? Let me write out what this means. So this means A, so this thing is equivalent to A times the Kummer of the first point plus B times the Kummer of the second point plus C times the Kummer of the third point. No. Is 0. Right? What is this? This is an equation in C to the 2G, well, in projective space, which doesn't matter. Okay? So what have we proven? We have proven the following theorem. This is called the phase trisecant identity. Despite its name of phase trisecant identity, it's really due to Gunning. It says the following. For any curve C, for any P, Q, R, S, the Kummer images of the 3 points written there in C to the 2G are collinear. Okay? Collinear. So that's what it means to be. 3 vectors are collinear. Let me draw a picture. Let me draw a picture. The coefficients are this A and B and C. I can calculate them. I don't care to calculate them. Sure, but don't. They have not played a role in the story I'm going to talk about, right? In principle, you can have a eager Krichever towards the end of his life was very interested in trying to further strengthen the result I'm going to state in 5 minutes, and then you may want to look at these coefficients. I won't be able to go in that direction. Okay, so let me draw a picture. This is C to the 2G, in case you couldn't identify it from my drawing, right? So that's a Kummer variety. That's a Kummer variety of a Jacobian of C, right? This notably has dimension equal to 2G. This notably has dimension G. And what I'm saying is that such triples of points lie on the line, right? So this is, there are 3 points, point 1, point 2, point 3. They lie on a line. So I do mean collinear. They lie on a line. Make sense? This is extremely surprising for high genus. Makes no difference. Up to you. Doesn't matter. If you rescale, nothing changes. Yes, and projective space makes no difference. Okay. Yes. Yes. But that's, yes. So okay. So this was a projective space at dimension 2 to the g minus 1. Yes. Okay. The point I want to make is different. So for g equal to 2, well, not very exciting. For g equal to 3, maybe not very exciting. Now suppose g is a million, right? You have a projective space of dimension 2 to a million minus 1. Huge, immense. And you have a 1,000-dimensional subspace, which is a Kuma variety, right? And now I want to draw a line, a line that intersects the Kuma variety in 3 points. Well, how do I do it? I take 1 point, I take another point. For any 2 points, I can draw a line. So this means the dimension of the secant variety of the Kummer is basically 1,000 for this point, 1,000 plus this point. Right? They both vary in the 1,000-dimensional space, plus 1 for the line, never mind. So it's like dimension 2,000. So I have a 2,000-dimensional secant variety and a 1,000-dimensional Kummer, and I'm asking for them to intersect in a 2 to the 1,000-dimensional space. I mean, highly unlikely, right? So this is highly unlikely. Okay, so the existence of such trisecants is very surprising. You would not expect that if you have a 1,000-dimensional variety in a 2 to the 1,000-dimensional space, it will not have any trisecant lines if you just write a variety at random. Okay. Not only that, I mean, you don't have one trisecant line; you have a 4-parameter family of trisecant lines, right? Yes, I have to choose them consistently. So I have to choose 1/2 of each point. I will be sloppy because if you look at how the Kummer map is really defined, I'm multiplying back by 2 anyway, right? So the way that I've chosen a specific basis for the sections of 2 theta, and there it's 2 tau comma 2 z. So the 2 will disappear. So in other words, you choose one, and then I don't need to make any choice. At the end of the day, there is no choice involved. Okay? Theorem. This is due to Gunning. If an abelian variety, a principally polarized abelian variety, is such that its Kummer image has a 1-dimensional family of trisecant lines. I'll write this theorem more formally tomorrow as the day after. So basically, I want the trisecant lines all to be obtained from this by just varying the point P, and everything else is fixed. So the trisecant lines are all translates of each other. Then A is a Jacobian for some curve C. This is in the early 1980s, maybe 1981. Yes? Moduli space of principally polarized abelian varieties of dimension G. So this is a solution of the Schottky problem. Okay? It tells you when an abelian variety, principally polarized abelian variety, is a Jacobian of a curve. It's a wonderful result, very famous. There is one caveat here. I have to give you a 1-dimensional family of trisecants to start with. And even though I'm not writing it here, I'm saying that I should just take this triple of points and translate this for all P. So basically, I'm already giving you a curve inside an abelian variety here. So I'm not just giving you an abelian variety, I'm giving you an abelian variety and the curve, and then this is the Jacobian of that curve. That's somehow wonderful, but you start with having a curve. if you think about the trisecant here, that's maybe very geometric, but maybe not very analytic. If you look at this equation here, this is an equation. It's some kind of equation for the theta function. I'm allowed to vary p, q, r, s along the curve. In particular, I can make them collide. I'll get derivatives. This will be a differential equation satisfied by the theta function in the limit. An interesting differential equation, which is where we'll go. So you can also have limits. So the next theorem in this direction was due to Welters, I think 1986 probably or so, is a germ of a one-dimensional family of trisecants suffices. Meaning, if you don't really have a one-dimensional family, but you have a germ, an infinitesimal formal germ, that's enough. Okay? It's sort of natural how you try to prove it. Well, you have a germ, why don't we extend it to an actual family and apply gunning? That's how you do it. I'm not going to tell you how. Welters, on the other hand, made a conjecture which says if the Kummer of A has one trisecant, A is a Jacobian of some curve. Okay? This somehow, even though innocuous looking, is a very different statement because you have no curve. You have no germ of a curve. You have nowhere to start, right? If you have a germ of a curve, okay, you make it into a geometric curve. The proof of Gunning's trisecant theorem really uses Matsusaka-Ran criterion about homology classes of curves that I will mention eventually. No. You have we'll always have a trisecant for dimension reasons, and all genus 2 abelian varieties are Jacobians. I'm being sloppy, so I should allow partial compactification of the model F abelian varieties. I'm not, never mind that, of the model F curves. So the curve C may not be smooth. Ignore it. So, and this is a theorem, this is a celebrated theorem of Krichever. Around, okay, maybe around 2015, depending on how you count time. Okay. So Krichever proved Welters' conjecture. He proved that if you have an abelian variety such that its Kummer image in projective space has one trisecant line, this abelian variety is a Jacobian. Okay. This, I'm writing this as one theorem, but you can imagine that there are various cases. There is this case, which I've just drawn, but there are more degenerate cases. So I have a family of trisecants, right? So I can have this trisecant, or I could have this trisecant, right? I'm drawing suggestive pictures. This is much higher dimension. But what I can do is, suppose I take these 2 points and bring them together. Then I'll get a trisecant that looks like that, right? It's a semi-degenerate trisecant, if you wish. So it's a line that's going to be tangent to the Kummer image at one point and is going to intersect it at another point, right? And of course, I can do this at this point. My drawing skills are going to leave me soon, but you know, I could also draw it at a nearby point. Again, there is a point of tangency and another point and so on, right? So there will also be a family of such things. These are going to arise when I have allowed a couple of points up there to come together, right? So you can see that the dimension of this family of such degenerate trisecants for a Jacobian is not 4, but smaller. But what I can also do is I can now make this come closer and closer to the curve, and eventually what I'll get is what is called a flex line. So this is tangency contact of multiplicity 3, also known as a flex line. So this means that the most degenerate trisecant is when I have a line in P2G minus 1, 2 to the G minus 1, which is tangent to the image of the Kummer map with multiplicity 3, right? So the statement here should be read as 3 separate statements. That if I have a fully discrete trisecant if I have a line which is tangent at one point, and if I have a flex line. In terms of equations for the theta function, this corresponds to a difference equation, to a difference differential equation, and to a fully differential equation. Okay, as we'll see. No, it's not allowed to go through a point which is singular on the Kuma varieties. There is an open conjecture in that direction. There is an open conjecture in that direction, which is related to this, which remains completely open and not understood, which I'm happy to tell you about privately, but not here. So this point, what Pasha is pointing out, of course, is that the Kuma variety is singular at the two torsion points. So the tangent space at the two torsion point at a singular point is a tricky business. So I should prohibit my trisecants to go through the two torsion points. There is something to be said there, but I'm not going to. So my plan, if I'm successful for the next 20 minutes plus 2 times 1.5 hours, is to prove the flex line case of this characterization. They're all different. The proofs are different. There is some step that I hopefully will try to demonstrate I somewhat understand for the flex case, which I don't really fully understand for the fully discrete case. There is some difference, just to warn you. There are separate papers. Okay? So the goal for the remaining 15 plus 2 times 90 minutes is to try to tell you a proof of this theorem. So I want to tell you a proof of this theorem of Krichever that if the Kuma image has one flex line, then you have a Jacobian. I will allow myself to use freely the theorem of Gunning, which I will not prove, which has a very nice proof. It's not very difficult, but it requires a whole set of techniques that we haven't developed. It's not hard. I mean, for an algebraic geometer today, it's not hard. When Gunning did this was a breakthrough, of course. But I can tell you how that sort of works. But as I wanted to emphasize here, the main difficulty is if I have one flex line or one trisecant, I have one point, I have no deformation. So somehow the key point is to start deforming this to construct at least an infinitesimal family of flex lines, trisecants, or whatnot. And that's what I'd like to tell you how that works, right? Because hopefully it's believable that once you have a curve, you're in better shape. I'll make some noises as to what you do then, but the main goal will be to just deform one flex to something. Okay? Any questions? Okay, so now we'll take a 2-3 minute break. I'll have some tea, I'll have some coffee, I'll erase the blackboard, and then we'll continue for another 10 minutes because what I'm going to do then is a completely different direction, but I want to start it today so that you are morally ready for tomorrow.
And I think I'll use this quick break to make some organizational announcements. Okay. First, tomorrow, after Sam's lecture, we would like to take a group photo. So please wear your Thursday's best. Okay. And for people who plan to go to the Great Wall today, I think BIMSA will buy tickets so that we don't have to form a line of 100 people. Okay? And we will need to find a way to pay BIMSA back because the conference fund cannot be used for excursion. It can be used for everything else, including buses to the wall, but not for the actual tickets. Okay? So I'll let you know about that. And if you plan to go to the wall, you do need to have your passport or a photo of your passport, I think usually suffices.
So maybe we can have a lecture at the top of the wall, then Vince can pay.
For the winter school that Kolya plans to organize. Okay, no, Pash, next time we will try to choose better season and then maybe find a better location and have lectures on top of the wall.
Okay, 1 minute to go.
Don't misunderstand the meaning of the word short break.
So
It's not a coffee break.
1 minute to go. In 1 minute, I'll be back at the blackboard.
And all those who play game.
Okay, and the short break is now over, and we continue.
Okay, so the reason I wanted to break is what I'm going to say now will look very different from everything we've done before, but this really is the underpinning of the techniques. And this is a technique of how you can get some solutions of some differential equations using some algebra geometric data. The setup is remarkably versatile, and this is a so-called Baker-Chiesa functions, which, to the best of my knowledge, were introduced by Krichever. I was not yet born when this was introduced, so this is certainly classical for me. You know, the definition of classical is everything before your PhD is classical. Everything before your birth is, you know, antique. But this is not. This is still being used, and this is super classical. So Baker-Chiesa functions due to Krichever. So the setup is curves. This is a construction using a curve. So I have a curve C. I have a point which I'll denote P on this curve, which is what we've been using. And let K, with apologies to you, K inverse, be the local coordinate, be a local coordinate, I'm sorry. On C around P. So that K of P is infinity. That's what I mean, right? So this, normal people don't write K inverse for a coordinate. Normal people write K for a coordinate. It's very important not to be normal here and do the right thing, okay? So this is the data. If you think about this, this is a lot of data. So the moduli space of curves is a finite dimensional space. I add a point that adds one complex dimension, no big deal. That's a lot of data. That's an infinite dimensional choice, right? I'm choosing a local coordinate to all orders in the expansion. So they say infinitely many terms in Taylor series, right? The space of such data is an infinite dimensional space which admits a forgetful map to the moduli of curves with infinite dimensional fibers, right? The fiber to MG1 is a space of all coordinates, which, you know, some linear space, well understood. So that's my data. Proposition, also called definition, it says the following: for any C, P, K inverse and any general divisor D equal to P1 plus dot 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 plus PG, there exists a unique function psi, which I'll write as psi of x and p. X is a complex variable called the Baker-Ahieser function such that first, psi is a meromorphic function on C minus P. It's a function on the curve with simple poles at D and holomorphic elsewhere on psi as an essential singularity at P, and I want to say what kind, and I'll prescribe it by saying what kills this essential singularity, such that psi of x p e to the minus k x is holomorphic around P and equal to 1 at P. Did I write some nonsense? Yes? And this is a function of z. Z is on the curve, right? So this means k of z times x, z. I think I'm good. So as z approaches the point P, z is a point on the curve, right? So, I mean, I don't want it as a notation eventually. I won't write it. Psi is a function of the curve. But since Pasha seemed confused, I wrote the z here. Maybe this means everybody else was confused. So psi is a function of P. When P is given, it doesn't vary anymore, right? But I want, for good reasons, to keep the dependence on P explicitly. It depends on a complex number x, which is a parameter, and depends on the point z on the curve. So this function is meromorphic outside of the point P. It has simple poles at D, and is holomorphic outside of P and D, right? And then this function has an essential singularity at z equal to P, right? And I want to tell you what kind of singularity it has. So I take this function, I multiply it by this gadget, where k is this coordinate, right? So this function also depends on k. I just don't want to put in the data, right? And I'm saying I take this function near z, and I multiply it by this expression here, k of z times x. X is my parameter, right? It's just a complex number, plays no role elsewhere. And then remember, k is equal to infinity at z, right? So this is e to the minus something going to infinity, right? So this kills the essential singularity. So I want to say basically that psi has the essential singularity. So basically I want to say psi has a form e to the k of z times x near P, right? That's what I'm trying to say. I'm trying to say it a bit more formally because I'd have to, if I write it this way, I'll have to explain what this wiggle here means, right? And that's what I mean, that if I take this and I multiply it by something which has an explicit, vanishing local in coordinate, this is holomorphic and normalized to be equal to 1 at P, okay? That's a proposition, which is a definition, right? So this defines the object called Baker here as a function. And that's the definition. The proposition is there exists a unique that guy, right? So I want to prove that proposition, and we'll be done for today. But is the statement clear? So this is a definition of a function on a curve depending on a bunch of parameters on x, p, z. Somehow I'm being very sloppy as to which parameters I write in the notation, which I don't, but there is a reason. So this defines a specific class of functions on curves with essential singularities, which is extremely useful, as you'll see, well, as I'll say in 2 words today and as I'll write next time. Okay? Any questions on the statement? So you have a function outside of, you have a curve. Outside of one point, it's just a meromorphic function. All good. I have prescribed it to have simple poles at D. D I've chosen to be general so that I don't have to worry about stuff. All points are distinct. The divisor D has degree G, which is why this works. And then I claim this is unique. So somehow prescribe, I'm saying that if I prescribe an essential singularity of that kind, there exists a unique function with that essential singularity and G simple poles at prescribed points. That's what this says. Fair enough? Proof. So the easy part is uniqueness. So if psi are two such things, then of course if I take psi and divide it by psi prime, probably can't read anymore, then this has no essential singularity. Oh, yes, because prime, well, next, I will not write psi prime at any point because this is not a derivative, okay? I will never write derivative as prime because I'll be taking x and y derivatives in it. But there is a generalization of this which will show up next when instead of x, I write x, y, and whatever here, and the singular part is prescribed more general. The proof will be the same. I don't want to do it more. Okay. So if I have two such functions, take their ratio. It has no essential singularity at p anymore, right? Because I've just canceled the essential singularity, and is in fact this ratio equal to 1 at p, and is holomorphic on c minus p. So this means is equal to 1, right? Because I've canceled all the simple poles. They're at the same points. The points p1, pg, means the d is not part of the notation, but I have fixed the d. Okay? Yes? Exercise. Yeah, I have to worry what happens about zeros and so on. So, okay? We'll return to this next time because I do want to say more about this. But this is roughly how it should go, right? So the point is when you're trying to prove some uniqueness like that, you basically say the essential singularity is gone, and then we'll use some Riemann-Roch. Okay? So you're right, of course. There are zeros and they will play a role. Never mind. Okay, now let me try to show why it exists. Existence. Well, you can try to prove existence, which is fun. But I can just tell you what psi of z is. It's the exponential of the integral from p to z of x times omega times theta of z minus d plus ux divided by theta of z minus d, where omega is a differential on C with a double pole of the form dk at P and holomorphic elsewhere, with all A periods 0, A, okay, and U is a vector of B periods of this omega. Okay? Yes? Hmm? Where is the differential equation? Yes? But I don't know, I don't yet know what the differential equation on C means. What do you mean by differential equation on a curve? I better differentiate with respect to something. I'm going to be differentiating with respect to x eventually. You're probably going the right way, but let's talk otherwise. I should be done in -2 minutes, so, which I'm aware of. So yes, I will worry about uniqueness next time. But let me try. And I'm not going to. I'm not going to prove that what I've just written has the correct thing, but I'll try to explain. So let's try to see what this looks like. So this guy here, this is going to vanish precisely when the point Z on the curve hits one of the points P1 through PG, right? By our discussion before, the zeros are these points. So this is certainly going to have simple poles where it should. Where the zeros will be, I don't know, but I don't particularly care because they're not prescribed. What will the essential singularity be? The essential singularity is controlled by this, right? That's the only place where it comes from. And it's your exercise to check that this is correct as stated. Dk, what is this dk? This is like the differential dz on the Riemann sphere near infinity. So it has a double pole. Since I've prescribed the coordinate k, this fixes what double pole it is, right? And then you need to prove, this uses Riemann's bilinear relations, that there exists a unique differential with a double pole of prescribed kind with all A periods 0. That's a general statement, that if you prescribe the singular parts of a differential with no residue, then there exists a unique such meromorphic differential with all A periods 0. Okay? And then you have to unravel why I'm writing this numerator in this nice way and what it has to do with the story and so on and so forth. Okay? Why should it be believable to you? Well, maybe it shouldn't, but there are two reasons. One, we somehow discussed how to construct every meromorphic function on a curve from theta functions. So that's a souped-up version. I've just added an explicit exponential factor to create the essential singularity. B, if you went yesterday to Pasha's exercise sessions, you've seen the genus 1 case of this. Okay? And locally, it's you've seen a specialized case of this when P is equal to P1 and under some assumption. So I should not be allowing P equal to P1 in this construction for it to be general and so on, but this is still in the same realm of possibilities. Of course, in this construction, you could take limits as D approaches some more special devices. We're not going to go that way. Okay? But the message is that you can just write an explicit function. And somehow, if you were Igor Krichever and you needed to write a function on the curve that satisfied necessary conditions, you do some magic, you write some differentials, you write some periods of some differentials, you write some theta functions, and you're done. Okay? So I will not prove that this satisfies all the right properties, but it does, right? That's the claim. Okay? And uniqueness uses the fact that this, everything I've written here somehow doesn't seem to know that this is a degree G divisor, except when I was writing this clearly has precisely G poles, right? But if you want to understand the whole story, it has to be precisely G poles, okay? So that's the story. Why is that useful? That's 1 minute and we're done. Well, by itself, maybe it's not so useful. It's just a function with an essential singularity. Who cares? But suppose I now take this guy and I take its derivative, but not with respect to Z, but with respect to X. What's going to happen? I've taken derivative with respect to x. Somehow this function, I haven't told you, but you can see it depends nicely on x. I mean, there is no problem to differentiate with respect to x. We'll be able to do that. So this is part of the statement, which I'm not officially declaring. But if I differentiate with respect to x, I'll get again a meromorphic function in the Riemann surface, which will again have an essential singularity, right? The essential singularity will be at the point P. If I differentiate with respect to x, k will come down, right? So the essential singularity will be the same as this times k. It will be killed by, I take out k. If I differentiate with respect to x twice, I'll get k squared, right? But then, if I take psi, and I take the second derivative of psi with respect to x, or if I take the first derivative with respect to x of psi, and then take the square, then you'll see that they have the same essential singularity. Well, maybe up to some constants, but not even that, near p, right? So I will have two different functions with the same essential singularity. Of course, I'm not saying this, but of course, I just chose some essential singularities. There is no reason I've chosen this one. I could do a much more general one. It should still be unique. So what this says is that these two guys should really be the same function by some uniqueness. Okay? I'm being sloppy. I will say it correctly tomorrow. Which allows me to see that the function psi constructed like that would satisfy a differential equation, which would be essentially this, right? Not quite true, as stated. Well, I just got a differential equation. I just solved some differential equation. That's not the differential equation I want to solve. We'll need to work harder. But this is where some solutions of differential equations will come. So basically, what this machinery says, you prescribe the essential singularity correctly, there'll be a unique solution. But then I'll be able to construct more than one solution by playing these games, and this will give me solutions of some differential equation. This, at the moment, is unrelated to trisecants, but trust me, they're showing up. Okay, so that's for tomorrow. So tomorrow we'll be differentiating functions and curves with essential singularities to our heart's content. And you will see differential operator L, L1, Ly, Lt, and all this stuff. Thank you.
Thank you. Any quick questions?
Yes. Well, U is a vector of B periods, right? So it's a point in the Jacobian. And X is a complex number. And the Jacobian is just, is covered by C to the G. So I'm perceiving all this as written in C to the G. So U is a vector. U is a G-dimensional vector, which I'm multiplying by a complex number. Okay? There is a reason I want to write this formula today, so that it sort of sinks a bit in your minds. I will do it again tomorrow, don't worry. More questions?
Let's go for the coffee break.